Hello, everyone. I'm Chen Long from Microsoft Research. And today I'm going to talk about a new specification for synthesizing analytical SQL. So SQL is the language for querying relational databases. For example, if this user has data that shows city, the quarter, and the number of people enrolled into some program from that city, and then the user, if interested to know how many people enrolled in the city program for city A, they can write a simple select from where query, no doubt. And if the user is interested in something else, like the total enrollment number for each city, they can group by city and calculate the sum. Also easy. But sometimes people want more, and those are people are app developers or like data scientists. What they want are something like, I want the total enrollment number at the end of each quarter, or I want to calculate the moving average, or I want the quarters with the highest enrollment number. In this case, you'll find SQL is quite annoying and sometimes impossible. So the thing that basic SQL is not really sufficient for those complex analytical tasks. So to solve this, there is a wonderful language to propose, is Analytical SQL. It's an extension of SQL with analytic functions. Let me use this cumulative sum as an example. So the user wants the total enrollment number at the end of each quarter. So given this table, what the user can do is to use this query. What this query is doing is to partition the table based on city and then calculate the cumulative sum of the enrollment over the quarters. As you can see here, for example, for city A and quarter 2, the number is 100 plus 200. So quite straightforward. So in fact, Analytical SQL is a very, very expressive and rich language for analytical tasks. It can support a lot of wonderful things, like argmax, percentile, rank, lead. But just as analytical tasks are typically hard, especially they're often used with advanced SQL features like join, everything. So it turned out to be hard to program with. But now we have it's important, data science need them, app builder need them, but they're also very hard to use. So the idea comes to use program synthesis. And now the question is, how about program by example? We have a lot of wonderful work on having program by example to solve those table manipulation tasks, and probably it's going to work, right? So let's take a look. So now I have a data set, slightly more complex than the last one because it's also split the city and quarter into groups based on their age group and has a city population here. So now can anyone take a look at the output example? Tell me what I'm doing. Yeah, roughly some percentage over something, but not really sure what percentage over what. So actually, let me just show you the close-hand magic here. So what the task is the user wants to do is to actually calculate the percentage of cumulative enrollment for over the city population at the end of each quarter. So to solve this task, there are 3 steps. First is to group by city and quarter to get the total enrollment number for both age groups, right? Combine the number together. And after that, we can partition by the city to get a cumulative sum for the over the quarters, like we did in the first table. And then after that, we can divide this cumulative sum over population. And so we get a percentage. This is a pretty complex task, but also not that complex if you look in this way. But if you're looking back to this input table and output table, like how can I tell, right? You can see there is a problem. It's a way of communication in that the user really spend a lot of time to do the hard work to calculate the examples required, calculate the example to create this output demonstration. But this process can be error-prone. But the thing is that the hard work does not really help. Now the synthesizer is having hard work try to guess what it's doing, what the percentage comes from. So it means it needs to explore a lot of search space, and the specification may even be ambiguous. So now you can see the tension here is that user is spending a lot of effort but does not pay back. So can we find a way to make the specification better? So let's see what we can do. If you think how users are actually creating those percentage number, this output example, they are actually going through the computation process themselves. They may write an expression, use Excel or some other tool to do that. Now the idea is that if the user is already creating this in a way, then why not just let the user demonstrate the computation process, not just the final value? And here, this is our key idea. So what we're proposing, the new specification for demonstrating analytical tasks, is to use computation demonstration. So what it looks like is something like this. So there are 3 aspects in this new specification. First, The demonstration is over the computation using cell-level expressions. The user don't try to simplify or evaluate the expression at the cell level to show their computation process to the synthesizer. And the second perspective is that we don't have to let user to create a full output example because the expression actually contains a lot of information about the computation. In this way, we are saving user some effort. And finally, in analytical task, the user actually typically are for aggregation or accumulate over a lot of values. So it would be ideal to just the user to demonstrate using part of the arguments in the expressions. This will make demonstration easier. So all three together just comes into this new specification, computation demonstration. So now we have a way to let users specify. But is this something that can let our synthesizer to comprehend easily? So now this comes to question, what is the criteria for a query to be correct with respect to this input table and demonstration E? So in program by example, the criteria is Qt should equal to E, right? But now here we need to extend this a little bit in the sense of computationally consistent. So let me try to break this down into 3 steps again. So the first thing is that when we are looking at evaluating a Q over input table, we should try to keep track of how the input values are computed so that we are having a weight comparable to the output example. This is what it looks like. So this is where applying the correct query Q into the input table. As you can see, instead of simplifying and calculating the final value, I'm trying to keep track of what the values, what the expression looks like at the cell level, so that at least we're comparable to the user's demonstration. And second thing is that remember that the user specification can be partial, right? So that we should capture this is the fact that E only need to match a subset of the demonstration. And finally, there is in terms of generalization here, if the user omits some parameter using those ellipses, then an expression with more parameters should be consistent with this, as long as the expression is the same. So if all these 3 criteria are satisfied, we can consider this Q to be a correct solution for this synthesis problem. Now we have this synthesis criteria, and what we can do is just to try to explore the search space to find a Q, satisfy those. And this should be a solution to this synthesis task. And there are a lot of ways to do this. One of my favorite ways to just do enumerative search. You have a bunch of operators, and the way you do is like starting from the input table, try to construct a bunch of like skeletons of those programs, and at every step, just try to instantiate some parameters with the like candidates based on the domain, and eventually until you find a program that is correct. This is a very straightforward process, but also very expensive. So the general idea is to try to prune those abstract programs, like partial programs, early, so that we can speed up. So for example, some programs are quite easy to tell. Like this group program, we can know that the output is only going to have 2 columns. So it's obviously wrong because our demonstration has 3 columns. This is basically type information of the table. And the second aspect you can do is take a look at that the output of this query is that because it's going to drop the CT column very early, but the output actually requires those AB value to appear. So by value analysis, we can know this program is also incorrect. But unfortunately, those are just a subset of program that can be easily analyzed. For example, given a program like this, we know it's incorrect, right? Because I spent a lot of time to introduce you this partition operator, but it does not appear here. But how can we tell? And so here comes the reasoning problem. Is a way for us to reason about this program behavior to prune it. So let's take a look in detail. Now we have input table T and output table E. How do we prune this Q? And the key idea is to use a process called abstract problem analysis. The idea is that if you take a look at output example E, it contains information of how values in T flows into E, right? And now if we can analyze abstractly, if this Qt data provenance or data flow is consistent with the demonstration, then we can tell it's correct or not. And because this query is incomplete, we cannot do this exactly. So what we're going to do is to over-approximate the data provenance, trying to analyze what a superset of operators that can flow into the output, so we can compare. Let me show you step by step. So first, we're going to run this table T through this group query. What we can tell is that no matter how the aggregation function or aggregation column is going to be, we can tell that the aggregated value must come from the values from the same group, because the group number is already determined. And now that we can look at second step, right? Now we're applying this arithmetic on top of the result. despite I don't know what the operation I'm going to do, I can tell the arithmetic is a column-wise operation, so you won't be able to use values from other rows. So it means, for example, for this CTA and quarter 4, the only value can be used is anything from the same row. But now if you can compare this against user demonstration, there is an issue. Because our demonstration actually requires a value called 1667 to come through to this cell to be used as a parameter. But from our analysis, this value has no chance to flow into this particular cell. It's basically because the group does not allow you to do cumulative sum like thing. So because of this, we can tell that no matter how this program is going to be instantiated, it has no way to conform our example. So we can prune it away. So now if we plug this in, we're able to basically solve this synthesis problem. And so basically, like given the input table, the user specified using computation demonstration, and our criteria to find a Q that is computationally consistent, and the algorithm is to do numeric search with after analysis to prune. So we did an evaluation first on the efficiency. We collect a benchmark with 60 online polls and 20 queries from TPC-DS, which is the Analytical SQL industrial benchmarks. And we evaluate comparing type, value, and provenance analysis. And here we're using demonstrations generated by sampling to evaluate the synthesis performance. So here I'm showing you a chart that shows x-axis is the time, and y-axis is number of benchmarks can be solved, split by easy and hard task and 3 baselines. As you can see that our tool called SQL is actually quite slightly faster on easier task, but on a faster task, we're not only significantly faster, but I can solve much more tasks. And when we look at the number of program visits in the search process, well, this is a box plot showing the number of program visited here. We can see it actually visits significantly less number of programs because of pruning power. And finally, we conduct user study to learn user experience with 6 tasks and 13 participants. We compare 3 ways of specification. One is using concrete value. Another is using computation demonstration with partial expression. Without partial expression, another using a standard demonstration. There are several things we learn from the users that are kind of interesting. So first, computation demonstration is typically faster for harder tasks, but for easier tasks, PBE is just straightforward, simple. They can eyeball and write it down, right? But in general, like despite sometimes it's slower, user feels they are telling this computer more, so they feel more confident. But on the other hand, we also discover expressions not really suit for all tasks, like count and rank. You can eyeball and write down the answer, but you don't know how to write down how it's computed. It's not obvious. So this probably means some combination of specification in the future. And finally, in terms of partial expression, it's reduced specific effort for long expressions. But some people actually find it might be tricky to know which one to omit. So this indicates an opportunity to inspect how user will create the demonstration than just what they need to provide. So basically, this is everything. Synthesizing analytical from computation demonstration. And the key position here is about a new specification for users to better communicate with system to solve the synthesis problem. Thank you, everyone.
Hi. There is a tool called Gauss in last Uppsala 21, and it also kind of uses similar kind of demonstration. Could you tell me the differences and similarities?
This is actually very interesting. I think Gauss is mostly focusing on like data transformation with typically one steps of aggregation. So in that case, users are actually able to specify the full expression better. So in some design here about partial expression as well as equivalence in terms of how partial expression is written, this is actually more flexible. Another interesting distinction is on the analysis done. In Gauss, it's depending on the program's, the structured expression to check consistency, but where we're abstracting away that, we're only tracking data provenance. This is more flexible, but we no longer assume that user will always put the same structure. I think both ways would be it would be interesting to combine, but the key thing here, can user provide structure consistently or not? This is kind of the main point.
Hey, thanks for a great talk. So you mentioned that some of the operations are not so easy to demonstrate in this way, like so count, for example, right? But the spreadsheet software has invented like all kinds of ways that users are already used to for demonstrating some, basically through the GUI, right? By selecting things and dragging things and stuff like that. Have you thought of like combining computation demonstrations with those kind of spreadsheet GUIs?
Yeah, absolutely. I think for a lot of operators like sum or average, it's very easy to use like spreadsheet expression. Just imagine they can apply this formula directly. But actually for rank, it's a very weird situation. Like we all know how things are ranked, but we never write expression unless we're computer scientists, right? I think this probably requires a different level of demonstration. Maybe you demonstrate 1 or 2 ranks as a value to combine together. But those are just really weird. Like users don't understand what expression is going to be. Yeah.
Yeah, thanks so much. Great work. I just had one kind of a hypothetical question, I guess, which is, so this work deals specifically with analytical SQL. I was wondering if you have any thoughts on whether or how this might extend to either other domains or even to just programming more generally in like general programming context.
This is a very good question. So analytical SQL is just a way for us to summarize what is computation intense demonstration. So in general, I think the key idea is to say if the user have a computation in their process, I mean, either in like data science or like in SQL or anything, like there should be a way to specify the computation process. I would say this thing is more focused on computation, not instead of an analytical SQL. Analytical SQL is just the domain we apply this to.
Okay, I also have a question, I guess, or several, but I'll just ask one for now. So you have here, I think, very interesting part here is this provenance abstraction that you actually are able to prune the search space by a lot, right? And there was also like type and value, and both have their strengths and weaknesses. Overall, this seems to be much stronger than the other ones, but are there cases where the other ones are better? Is it possible to combine them in certain ways to strengthen your results?
Yeah, so the key advantage of like provenance analysis is really dealing with kind of grouping and partitioning. It's kind of track where the data will flow is going to be. So in general, for other things, for example, like data reshaping, their provenance and value will be very similar. So, and also like if you are doing more like matrix style manipulation, then type will be actually very strong because in that case, tracking the provenance or the value will be exponential. So in this particular context, provenance is definitely the best. But I would say if we combine like reshaping and analytical together, probably we need to decide, okay, when to use what. Maybe to do all together. It's not too expensive if you can prove more, right?
Thank you. Okay, let's thank the speaker again. And thank you.
Yeah, thank you, everyone.